Let me introduce myself before I get into this talk. My name is Krishna Raj, and I've been with VMware for close to 8 years now, and I work on the performance group. And I focus on the platform performance, which includes the CPU scheduler, memory scheduler, virtual machine monitor, and all core platform features. I worked on the VMware fault tolerance feature that was introduced with vSphere 4.0, and I also worked on VMI para-virtualization performance. This is like 3-4 years back. And prior to that, I have a lot of experience in performance troubleshooting. I used to deal with customer cases, which internally gets reported to us, and I used to help in troubleshooting performance problems and stuff like that. So this talk is meant for complete advanced users, which means I assume that you have some sort of familiarity with ESXTOP, what the tool does, and how to use it at the basic level. So I'm not going to cover any of the basics information, and I'm going to jump straight into very advanced topics. And depending upon how technical depth you guys want, I can go as much as you guys want. So can I ask one question so that I can gauge the audience? How many of you guys have seen my previous ESXTOP sessions at VMworld? Okay, none. All right. So then I'll probably go a little less in depth. Okay, so there's a bunch of ESXTOP resources available on the web. The first one is the ESXTOP manual. If you have the ESX service console, you can do man ESXTOP. It pretty much talks about the manual page. But if you're running ESXi, then you can get the man page from this location. You can download this, you can print it. And then we actually maintain a couple of community documents, and these actually are, they go into great depth about what the counters are, how those counters are calculated, what scenarios you can use as counters. And we recently updated this document for ESX 4.1, because in ESX 4.1, we added a whole bunch of new ESXTOP counters. And these are the links for my previous 2 VMworld talks. And I highly encourage you to go through these talks, because these talks covers a lot of troubleshooting scenarios, which I'm not going to talk in this presentation. They talk about how do you detect memory overcommitment issues, how do you detect CPU problems, how do you know whether it's a CPU contention issue, or whether you are hitting a resource limit because you have set a resource limit on your resource pool. And it talks about how do you find out HPA saturation issues, how do you figure out whether you have problems with your storage array, and things like that. There's a lot of content in these 2 talks, so I highly encourage you to look at those talks, in addition to this one. So in this talk, I'm going to talk about the 10 things that you need to know about ESXTOP as an advanced user. And I'm assuming that you know the basic stuff, so I'm going to only talk about subtle things that people might miss when they use ESXTOP. I want to talk about all the new features introduced with ESX 4.1, all the new counters that were added, and what's the meaning of those counters that I'm going to cover. Then I'm going to talk about more troubleshooting examples using those new counters. Then at the end of the talk, I'm going to talk about the diagnostic tools apart from ESXTOP. So for a vast majority of you, I would say greater than 95% of your performance problems can be solved just by using ESXTOP. You don't need any other tool. As long as you understand the counters, as long as you know how the tool works, you could solve majority of the problems just using ESXTOP. But there might be some occasional instances, hard to trace problems, very difficult issues. You may have to resort to other advanced tools. So I'm going to give you a brief introduction into those tools and what they collect, but I'm not going to go into those great details. These tools are meant for the technical support folks. So if you call them up and they're going to ask you to collect these data, then you probably wouldn't know what they're asking you to collect. So I'm just going to give you an introduction on those. Okay, 10 things that you need to know about ESXTOP. The first and foremost is that ESXTOP does not create performance metrics. The raw performance metrics are already there in the VM kernel, and it is in a place called VM kernel system info node, or otherwise called as VSI nodes. So VSI node is somewhat similar to proc node in Linux, if you're familiar with Linux. So in proc node in Linux, you can go and read a lot of statistics about your Linux system. You can also change and tune the parameters of your Linux system. So the VSI node is the proc node equivalent in VM kernel. It allows you to do the same thing. The difference is ESXTOP only reads those counters. It doesn't go and modifies those counters. Now, if you've used the vCenter client UI interface, that you might have seen an option called VM kernel advanced settings, and you can go and change a bunch of tunable parameters, and some KB articles would recommend you to change those parameters. Those parameters are all changed through the VSI node. So that writes into those nodes, but ESXTOP only reads from those nodes. So the point I wanted to tell you here is that the raw counters are already there in VM kernel. ESXTOP mines these counters and then does a little bit of math, and then it shows it in a format that you can understand, or because the raw counters are very hard to understand. I know even the ESXTOP counters can be hard to understand for many of you, but the raw counters are much more difficult. Another subtle point is that ESXTOP can show new counters from an older ESX system because many of the raw counters might be existing even on the older system. So if you use the latest version of ESXTOP, let's say your system is still in 4.0, but let's say you downloaded the 4.1 ESXTOP, you can connect your older version of ESX, and you probably might see some of these counters because those raw counters are there even in 4.0. Second thing is how the counter values are created, right? There are three different kind of counters I could think of from ESX standpoint. One is many of the counters have static values. They don't change. They don't change during the lifetime of the ESX box or the lifetime of the VM that is running. So to give you an example, every VM has a world ID, a group ID, the VM name. These are static information. So ESXTOP just reads them and just shows them as it is. But there are many counters that increment in a linear fashion. They just increment in the VM kernel just keeps on adding those counters ever since the machine was booted on. To give you an example, the SCSI commands that is issued on the ESX host, that counter just linearly increments. So if you started a system, it might have a value of 1,000, and then after 5 hours, it may have a value of 50,000. After several days, it might have like 500,000. So what ESXTOP does is it does not show you the absolute value. What it looks for is at snapshot 1, it looks at the value. Snapshot 2 looks at the value, subtracts the value, divides that by the refresh interval that you have set. The default refresh interval is 5 seconds, and that's what it shows as commands per second. So this is true for a lot of counters. So commands per second, reads per second, writes per second are one example. Actually, this is true even for metrics like percentage used, percentage run, percentage sys. Any percentage metric that you're seeing in ESXTOP are also calculated in a similar fashion. So to give you an example, if a CPU usage is 50%, let's say, what that means is in the last 5 seconds, the CPU occupancy time was 50%. In the last 5 seconds, you are using the CPU for 2.5 seconds. That's what 50% means. Now, if your refresh interval is, let's say, is 10 seconds, and if your CPU utilization is 50% again, which means in the last 10 seconds, you have used the CPU for 5 seconds. And these 5 seconds could be contiguous time. It could be in a one chunk, or it could be spread over entire 10 seconds. It could be the first half, it could be the later half. You don't get those information. So the higher the refresh interval you have, you lose the granularity of the information. You don't know when exactly the CPU was busy and when it was idle, but you just get the trend. So to illustrate this point, I want to add this. The third point that I want to make here is that if you're going to plot some information using the ESXTOP data, actually this is true not just for ESXTOP, for any performance data, the sampling frequency or the refresh interval that you're using is very important because that controls how the data is going to look. So to give you an example, these two data are exactly identical. They are CPU utilization of a host, which is kind of spiky in nature, but each was collected with different refresh interval. One was collected with 2 seconds, another one was collected with 5 seconds, same exact system. The difference you notice is that when you're collecting at a much granular interval, you know the spikes and the troughs. But when you're collecting at the 10-second interval, that kind of averages out because you're looking at the 10-second much higher window. So this is an important point to note because depending upon what kind of performance problem you're trying to solve, sometimes you might need a much more granular refresh interval. In some cases, it's okay to have a 10-second refresh interval. The default is 5 seconds, and the lowest that you can have is 2 seconds. That's why I wanted to show you this spectrum. The other thing you need to know about is counter normalization. This is something a lot of people get confused when they first use ESXTOP. All the counters which are shown in the ESXTOP screen are basically cumulative counters. The reason is because ESXTOP groups a bunch of things which are related into something called a scheduling group. So for VM, there is a slush VM here. A slush VM is not just made of one process. It is made of multiple processes. And the term that we use in VM kernel is called world. Processes in VM kernel is called as worlds. So here it shows it's 100% used, right? Does that mean this VM is completely CPU saturated? Can you say that from the screen? Actually not. You cannot conclude it because you don't know whether this is a 1 vCPU VM or a 2 vCPU VM. This 100% could be coming because you might have a 2 vCPU VM and each vCPU is consuming 50%. So it might show 100% because the stats it shows is cumulative for the entire group. So to know how many worlds are there in this screen, there is a column, NWD, which tells you how many worlds are there in this group. So it shows there are 3 worlds in this. So this value should be normalized for 300% because the number of worlds is 3. So to give you an example, there is also another column called weight, percentage weight, which it shows as 200%. And again, I've seen this in the forums. A lot of people ask this question, why this wait time is so high? Why it is like 300%? Why it is 700%? If you have an 8 vCPU VM, you might see 700 or 800%. The reason is, again, this is all cumulative stats. And also, wait time also includes the idle time of your host. So if your system is completely idle, you would see a lot of wait time. So that's completely normal. You don't have to worry about that. So to confirm whether this VM is actually CPU saturated or not, or to know whether it's a SMP VM or a UP VM, the way you do it is you need to expand this group. To do that, you can press the E key in ESXTOP, and then it will ask for the group ID. So in this case, you enter a group ID of 6375. Once you enter the group ID, so actually I want to point you out, the group ID is actually there in this output here, which I haven't marked it here. So 6375, so you enter the 6375 here. Once you enter the group ID, you expand it. And you expand it to the individual worlds which this VM is composed of. And now you see the number of worlds count is 1. And then now you see the split time for the weight. You see it's 99.99 for the 2 worlds. And this VM, this vCPU world is having 0 wait time. And it's consuming all of this CPU utilization. So this is a key vCPU world that you should be monitoring for because this is your virtual machine's vCPU. So this confirms that, yes, you are indeed CPU saturated. The previous screen kind of hinted you that it's CPU saturated, but by expanding it, you can confirm that it's actually CPU saturated. Okay, having said that, percentage used could still be greater than 100. So the previous example showed that it could be greater than 100 because you're accounting it for multiple worlds. But even in expanded view, the percentage used can be greater than 100. And there are a couple of reasons for it. One is your processor could be running in a much higher clock frequency than its base frequency is. And that feature is called as Intel Turbo Boost, which was introduced apparently in Intel processor on Nehalem systems. So for instance, if your clock frequency is 3 gigahertz, on some occasions, the clock frequency can jump to 3.5 gigahertz. And it depends on the power consumption on your processor, how idle your other cores are. If you have a 4-core machine, and if the 3 cores are idle, then the 1 core on the system can increase its clock speed. That's how the Turbo Boost feature works. So if you're running at 3.5 gigahertz, then the percentage used can go above 100. So that's one reason. But a more common reason why a percentage used can exceed 100 is that sometimes a work can be done for a VM on a different core than where the VM is running. So, for instance, a VM could run, a 1 vCPU VM could be running on, let's say, processor 1. VM kernel can do a job on a different core, processing core, on behalf of this VM, and then it can charge those CPU cycles that it did back to the VM. So this is very useful. This is another reason why sometimes your VM performance can actually outperform your native performance if you compare one vCPU VM and a one physical CPU box. So how do you find out if that is actually happening? To illustrate that, here I see 119%. It's definitely more than 100%. But there is a clue here. The clue is you see the percentage run. The percentage run is 33%. What that means is this VM is running only 33% of its time. The vCPU is spending only 33% of its time on the physical CPU, but its overall CPU consumption is greater than 100, which means it's coming from somewhere else. And that is coming from the system time. The system time is a time spent by the VM kernel on behalf of a particular VM. So the way I simulated this is by running Windows 2003 on an NFS data store. And this NFS data store is managed by VM kernel. So any I/O that you do on the NFS data store, the VM does some I/O to the NFS data store. The VM point of view, it's a local SCSI disk, so it does just as an I/O, but the VMDK file is actually residing on an NFS data store. The processing for that happens on a different core. VM kernel does the processing, but VM kernel charges those CPU cycles back to the VM. So that's why you see an increased CPU utilization. And to simulate this problem, I need to really stress the system to the maximum. So I was doing a lot of I/O inside the VM, and I was driving up to like 4.5 gigabits of network traffic on my NFS data store. So that's why I was able to drive the percentage system to go up. So you expand the screen, and you actually confirm it that, yes, 95% of system time. VM is spending only 34%. So in this case, if you go to the guest OS and if you run the CPU utilization metric, you only see around 35%. But the actual consumption of the host is 120%. So system time in your environment should be less than like 20% for heavy I/O intensive workloads. This is like an extreme case scenario that I kind of simulated. In fact, most of my examples are all very crafted examples just to illustrate the point. Okay, the other point is batch mode. So ESXTOP has this mode called batch mode where you can collect your statistics in a CSV file format, and then you can do post-processing of this batch mode data. Now, batch mode has an interesting property. ESXTOP produces a CSV file which is compatible with Windows perfmon utility. So I don't know how many of you are familiar with Windows perfmon, but Windows perfmon is a program which can give you statistics about your Windows system. It can show live statistics, or it can also show statistics from a CSV file. So we produce a CSV file which is compatible with Windows perfmon. Then you can go to the Windows perfmon, and you can load the CSV file and actually show your ESX statistics instead of the Windows statistics. But the CSV file compatibility requires that you have a fixed number of columns. So the way we do it is ESXTOP has rows and columns, right? It converts all the rows also into columns when you want to make a CSV file because your columns are different time snapshots. Every 5 seconds you're collecting, so the columns are repeated. So we take all the rows, convert them into columns, and then you have more number of rows. In any case, the columns is fixed, which means if you run ESXTOP in batch mode, and after that you power on a new VM, that VM data will not be collected because we have to fix the entities that we are collecting. So that's one thing a lot of people run into because they start the batch mode and then they power on the VM to do some experiment and they don't get the data. The other thing is when you run it in batch mode, it only collects the counters, the default counters, which are specified in the configuration file. If you want to bypass it, if you want to collect all the counters, then you can pass the -a option. The last point is that counter names in batch mode could be slightly different. They are not the exact namings used for the interactive mode. If you're seeing percentage used in the interactive mode, in batch mode it might be called as processor utilization or something like that. So the community document that I pointed in the beginning of the slide has a table which explains what's the corresponding names. The name change is done because of the perfmon compatibility reasons. Okay, so I told you about perfmon. So this is how you launch perfmon in Windows. So you can do start run perfmon. You should launch this literally. You click on the cylinder icon to specify that you want the data from a local source, not from a live system. You specify the source. You load the CSV file. Once you load it, now you can right-click and you can add counters on the chart. And the counters are actually now coming from the CSV file. And you get to select what performance object you want to collect, like CPU, memory, disk, and what counters you want to see. And you can even get the counters for a specific instance, like whether for a particular VM, you're looking for counters. And all the charts you can see, it gives you average value here. What was the last value? It gives a lot of interesting statistics. The other interesting cool thing about this is you can also trim your data. If you have collected data for like 30 minutes and you're interested about the average CPU utilization in the middle portion, like 10 minutes of your run, then you can use a time slider here, and then you can adjust the time. Then your graph will change, and then you can get all your statistics on that. And then if you want, you can even save that file, save that constructed data point into another CSV file. So you don't have to have huge CSV files. You can chop them into smaller ones. We also have a tool in our website, labs.vmware.com. So labs.vmware.com is VMware's pet projects, toy projects, usually done by the people within our group and people in other groups within VMware. So this is called ESXTOP. This is a Python-based program. It can load the CSV file, and it can do this plotting. So it's kind of similar to perfmon. The only thing is this is supposedly much faster than perfmon. It loads. It can handle really large CSV files. And also, this runs on Linux. So you don't need a Windows to look at your CSV files. All right. So next, I want to talk about I/O latencies. This is, again, a very subtle point. A lot of people can miss it. So when you're doing I/O, the latency is measured per command. So your refresh interval doesn't really matter. Let's say your refresh interval is 10 seconds. In the 10-second period, you did only one I/O. That doesn't mean when your ESXTOP is reporting, yes, I did only one I/O out of 10 seconds, and it took so much time. It's not going to dilute your latency. The latency is measured per command. If you did only one I/O and the latency is like 10 milliseconds, 10-second refresh interval, it's still going to be reported as 10 milliseconds. If it is a 5-second refresh interval, it's also going to be reported as 10 milliseconds because it's measured per command. But the number of I/Os that you do within a window is definitely depend upon the workload. 10-second, the VM might probably do 100 I/Os. The first 5 seconds, maybe they did 10 I/Os. The burstiness nature of how frequently it issues I/Os is application and VM dependent. So that might change your average value because when you do 10 I/Os, the latency could be different. When you do 100 I/Os, the latencies could be different. So that can affect the latencies. The other thing is that we actually show latencies in different viewpoints. ESXTOP has the ability to show latency from the adapter point of view, which means all the I/Os which goes through the HBA. Or you can show the latencies from the LUN point of view, that is all the I/O going to a particular LUN. Because an adapter services multiple LUNs, then you can narrow it down, say, okay, this LUN I'm interested in, or you can even narrow it down to a particular VM. But remember, a VM can have virtual disks, which can be on different LUNs too. So there's all different sort of combinations which are possible. So the point I want to illustrate is that the latency that you see in a particular view may not be the same in other views because you are looking at different groups of I/Os. In adapter view, you're looking at all the I/O which is going to the adapter, which includes every other VM and non-VM I/O, all the I/O which you're doing in the service console, everything goes to that. When you're looking at VM, you're only looking at the VM I/O. When you're looking at a LUN, you're looking at all the I/O going to the LUN. So the latencies can be different. They don't have to be the same. So don't assume that. You look at the adapter view, the latency is fine, and don't assume that your applications are fine. They may or may not be fine because your workload can have bad latencies, and it could be hidden by good latencies by other VMs. And in adapter view, it might get diluted because we are reporting the average. Okay, the other thing is we have a tool called ESXTOP, which is the remote version of ESXTOP, which can be used to connect to a remote ESX host, and you can get statistics remotely. So this is necessary because we announced in this VM build that we are moving away from the service console-based ESX, though everything is going to be ESXi-based in the future. So we have this utility, and this utility is shipped as part of a virtual appliance that you can download, and you can connect remotely. There are two nice properties about this utility. One is it can connect to multiple different ESX hosts using a single binary. And it also works across different versions. You can connect to ESX35, ESX40, 4.1, and so on. The other advantage is that ESXTOP also can authenticate itself with vCenter, instead of authenticates itself against the ESX host, which means you don't need root privileges to run ESXTOP. Yes?
With the new integration of the Active Directory in ESX, can we still go against those, or does it
still the Active Directory integration with the vCenter server or with the ESX? Okay, so this will go through whatever authentication mechanism that you've configured. If you're configuring to ESX host, whatever authentication you use, that is what it'll use.
Can you repeat the question for the record?
So the question that it was asking is, if I use the Active Directory for my ESX host, will that be used for authentication? And the answer is yes. Whatever authentication mechanism you use, that will be automatically used. That is only if you connect to the ESX host. If you're connecting to the vCenter, similarly, whatever authentication mechanism vCenter uses, it just uses that. Okay, the last point I want to make is that this is the Einstein principle of uncertainty. You could think of it like that. Basically, when you're probing a system for measurement, you are actually disturbing the system because the act of probing a system itself adds to some CPU cost. So to illustrate this example, I wanted to show you an extreme case where ESXTOP can itself consume a lot of CPU cycles. So I took a host and I ran 512 VMs. The maximum number of VMs that we support is 320 on a single host. So but I chose a host with 512 VMs. That host also has a lot of LUNs, a lot of virtual disks, a lot of virtual NICs, because statistics for all of these are collected by ESXTOP. So you're collecting a boatload of statistics. Now, when you look at the screenshot, you see that ESXTOP can consume as high as 50% CPU because you're constantly looking at statistics. You're constantly looking whether new VMs are getting powered on, and you're scanning the system to collect statistics. And I'm collecting at a much higher refresh interval. So this is bad, right? So you don't want your monitoring program to consume a lot of CPU. The other point I want to show is that is with ESXTOP. What about remote ESXTOP? Because remote ESXTOP runs locally on your box. Right? So would it consume CPU on the ESX host? Yes. The answer is yes, because it still gets the statistics through an agent which is running on the ESX host, and the agent is called hostd. So there you would see when you use remote ESXTOP, hostd is consuming CPU cycles. In both cases, hostd consumes CPU cycles even here. In both cases, it consumes CPU cycles. hostd has its own work to do when you have large amount of VMs. So this is like an extreme crafted scenario where you can see high CPU utilization. So how do you solve this problem? One is don't collect all the statistics. Just focus your collection to the statistics that you're interested in. That will greatly reduce your CPU utilization. Second one is you can reduce the refresh interval. You don't want to collect every 2 seconds for all the 512 VMs. That will be like a lot of data. The third one you can do is we have an option called as log statistics -L. What this does is it basically, when it launches for the first time, it looks at all the things that needs to collect information, and it records that information, and it collects statistics only for those entities. So which means if you power on a new VM, or you added a new LUN to the host, or you created a new data store, those statistics won't be collected. Whatever was there at the launch time, only those statistics will be collected. This is very similar to the batch mode. This is what happens in batch mode too. But this greatly reduces your CPU utilization. So in this case, you would see like it drops down to 18%. So in worst case scenario, you could use this option. Okay, so I think that concludes that section. So we'll talk about the new features in ESX 4.1. So before going to the news features, I just want to show this slide for people who are completely new to ESXTOP. We have a bunch of screens in ESXTOP. Each screen shows you different metrics. We have a screen for CPU, memory, networking, and we had new screens in different versions of ESX. 3.5, we had a couple of new screens. So the latest one is this power management screen, which can show you power management statistics on your ESXOs. To highlight this, I just want to show you one more graphic here, which basically shows you that how exhaustive ESXTOP is when it comes to collecting statistics of all your ESX system. We have 3 different screens just for CPU. We have 3 different screens just for your storage. We have a screen for virtual switch. We just need one screen for virtual switch because all the traffic in your ESX host goes to the virtual switch. Whatever traffic it is, everything goes to the virtual switch. One screen for memory scheduler. So it was pretty exhaustive in terms of what we collect statistics-wise. So I'm going to talk about the new things in 4.1. So the first thing we did is, what if I want to narrow down my statistics collection, or I don't want to look at like if you have a host with 100 VMs, I don't want to look at statistics of all of them. If I'm focusing on one particular VM, I want everything else to disappear in ESXTOP. So you can do that by pressing the L key, and you can specify the group ID, 6029. Now this group ID can be a VM's group ID, or it could be something else which is running on the ESX host. So in this case, I've chose the agent's group ID, the host agent's group ID, 6029. And now everything disappears, and only that group gets displayed. So this will be very useful when you are focusing on a particular VM. You don't want the other clutter. What about a case where you want to look at the top 5 CPU consumers? You don't want everything else. You want, if you're running 100 VMs, again, you have 100 rows, right, basically. So you want only the top 5. So you can press the hash key, and then you can enter the number of instances you want to watch. And then again, the screen gets limited to the top 5. Of course, you can sort these results with different. You can sort it by percentage use, percentage run, percentage weight. There's a separate key where you can specify your sort option. Okay, now this is completely not recommended. This is meant purely for technical support. And this is a feature to kill a particular world which is running, which is like killing a process, basically. The way you do it is, again, you press the K key, and you can specify the world ID, and then the world gets killed. To aid this process, we also added a new field called LWID, which stands for World Leader ID. So world leader is basically the parent process. So if you kill the parent process, all the child process gets killed automatically. So this is important if you want to kill everything in a neat fashion. So we added this. Again, completely not recommended, and this is also not supported with ESXTOP for security reasons, because ESXTOP, people use it for monitoring purposes, and you don't want a monitoring person to go and kill all your VMs. So. All right, then we added the new screen, power management screen, which gives you the information about the power state of your processors. So the rows in the screen are the CPUs. So you have 16 CPU on this box. And the columns tells you the residency time of this processor. So I'll explain what these are. So the first thing is called C states. C states are processor's state of whether it's busy or idle. C0 means the processor is busy, completely busy. When it's busy, it doesn't do any power saving. C1 means the processor is idle. And when it's idle, we issue an instruction, not just we, any operating system issues in this instruction called halt. When you do a halt instruction to the processor knows, you know what, I had nothing to do, let me go into a low power consumption state. That is C1. The newer processor also has something called a C2, which is a deep halt, which can put the processor in a much more deeper halted state where you might flush the cache of the processor and things like that to save power consumption. But if you are in a deep sleep state, not a sleep state, sorry, a deep halt state, then if you suddenly want to run the CPU, then you have a slight latency. So we don't go into the deep halt state. Currently, ESX uses only C1 state. It doesn't use the C2. But in the future, when we do active power management, we might do C2. So in this case, the screenshot shows that all these processors are in C1 state. 100% C1 state, which means it's an idle system, completely idle. Yes?
If you put a CPU into default, will it still show up in inventory, or does that affect you at all?
Okay, the question is, if you put the processor in a default state, will it appear in the inventory? Yes, absolutely yes. So default is not, you don't think has this like your suspend operation in your laptop. It's not, this is like at a much faster level. This is like, we are talking about delays of like few hundred nanoseconds. So the process still be available, but it'll be little inactive, and then you bring it back. So that's what the deep sleep is. Anyway, we don't use the default as of now, but we might use it in the future. The second power-saving consumption mechanism is the P states. P states is about the processor clock frequency. So when I say P0, it means you are at the highest rated clock frequency. So if your processor speed is 3 gigahertz, then P0 is 3 gigahertz. But processor can also dial down their frequency to different levels. So let's say you're going to 2.9, then it's P1. If it's 2.8, it's P2, and so on. So this processor has supports for like 12 different states from P0 to P11. But the P11 is the lowest state, lowest clock frequency, which could be like 1.5 gigahertz. So this tells you what is the residency time of your current processor. Now, if you see here, the residency time is all in P0, which means you're using the highest clock frequency, 3 gigahertz, which means CPU frequency scaling is not active. If you enable power management in ESX, then you would see when it's idle, it'll jump to P12, P11, so that you dial down your clock frequency. That also consumes, reduces your power consumption. But if your CPU becomes busy, then it'll jump back to P0. All right. We also show the power usage, the overall power usage on your system from querying the sensors from your system. So here it shows 228 watts. So that's actually coming from the sensors from the motherboard. So if your hardware is supported, then it will show up. If you have a white box, then it won't show up. Okay. Apart from looking at power information from a processor perspective, we can also look at power information from a virtual machine perspective. So now we added this experimental counter called as power usage for the VMs, and you can see this in the CPU screen. So when you enable this option, we can actually charge a particular VM for power usage based on its CPU utilization. So now if you are going to do chargeback, you can go and tell your customer, say, you know what, this particular VM is consuming a lot of power, shut it down, it's useless. So that kind of reporting is now available. Actually, this is also available in the performance charts in the vCenter also. So you can look at this information in both places. It's marked as experimental because we're still trying to tune it. It's kind of an approximation. We are tuning the algorithm to make it more and more accurate. All right. Then there are new metrics that are added in CPU screen. We have like 3 different metrics. One is called lat-C. Lat-C implies what is the latency that you have added to your VM due to a CPU resource issue. The CPU resource issue could be ready time. It could be because you have you're scheduling 2 VMs into the same core because they are running on different logical CPUs but on the same core. It could be because you have exceeded your max limit set for the VM. If you set your max limit to be 2.5 gigahertz, and if your VM wants to use more than 2.5 gigahertz, then it might show as lat-C as well. We added a similar counter for memory-related issue. This is how much time this VM was not scheduled because of a memory contention issue. That is, if you're swapping at the host level, then the VM is actually basically is not running when it is swapping. So that time will be accounted as the lat-M. The third counter, demand, tells you what is the moving average CPU utilization of this VM in the last 1 minute. Now, this is different from percentage used because percentage used tells you what's the CPU usage in your last refresh interval. When you see a percentage use as 50%, that is for the last 5 seconds of the snapshot that you collected. But what was the trend in the last 1 minute? It may be going up and down. So what's the overall trend? That's what the demand is. And then we have this counter called EMIN, which is estimated minimum, which is the minimum CPU resource utilization in megahertz that the VM is guaranteed to get when you have resource contention. If you load your system completely with all virtual machines, everything is burning CPU cycles, even in that scenario, this VM is guaranteed to get this much amount of CPU cycles in megahertz. So this is determined based on the reservation that you set for the VM, and it also depends on the share settings that you have. So it's a calculated value from your reservation and the share. This is the resultant value that you're guaranteeing to this VM. Okay, memory screen. So as you know, in vSphere 4.1, or as you may or may not know, in vSphere 4.1, we added support for memory compression. So we added a bunch of counters for memory compression as well. But before that, I want to talk about one more counter, which can be useful for a lot of folks. So copy on write. Copy on write means copy on write is a technique which is used to make page sharing work. So if you're sharing a page, two machines are sharing the same page. If one virtual machine is modifying that page, when it's modifying the page, we actually make a copy, separate copy, just for that virtual machine, so that the page sharing is completely transparent, because you can't modify somebody else's page, right? So we do copy on write. So copy on write stands for page sharing. In other words, it's an internal terminology. So this counter tells you amount of memory that are potentially shareable but are not shared right now. The reason for this is, if you have a system which has support for Intel EPT or AMD ANPT, we use large pages for the VM by default. And when we use large pages, we don't do page sharing. We delay page sharing. We do page sharing when there is memory overcommitment. When there is memory overcommitment, we break the large pages into small pages, and then we do page sharing. But we maintain a hint to see if any pages are potentially shareable or not. And we keep that information. So this counter tells you what is the potential page sharing benefits you would get when you actually overcommit your system. When you put more and more VMs in the system, this amount of memory can be potentially shared because we found hints for sharing them. And so it gives you the capacity of how much overcommitment you can do. The other counter is cache size and cache use. This is for the compression cache. The way compression works in 4.1 is that for every VM, we reserve like 10% of its memory. I shouldn't use the word reserve. I should say we keep aside 10% of the VM's memory for compression cache. And any pages which are needs to be swapped out, even before swapping out, we see whether it can be compressed. If it can be compressed really well, then we put them in the compression cache. So this tells you how much of this compression cache is getting used, the cache size and the cache used. And these counters, zip and unzip per second, actually tells you what is the compression activity, the decompression activity. And the top line also shows you how much pages have been saved because of compression. So here it shows like almost 2 gigs of pages have been saved by compressing them. Okay. Now this is my favorite stat, which is added in network screen. So we added a counter to see how many multicast packets are being transmitted and received from within a VM. So this will be useful for networking folks who are troubleshooting networking problems related to multicasting. If you use Microsoft Network Load Balancing, it actually can operate in multicast or broadcast mode. So you can find out whether the VM is receiving and sending multicast packets. Similarly, we also show the broadcast packet counts being sent and received. Again, this will be useful. If your network is misconfigured, it can send you broadcast storms, and you can actually see those packets going in for all the virtual machines. So this is a way to alert your network admins that something bad is going on. Ideally, you shouldn't be seeing a lot of broadcast packets. Okay. This is also a very interesting counter for a lot of reasons. It's SCSI reservation and SCSI conflicts. Reservations is basically a mechanism used to lock a particular LUN when you are doing an operation which is very sensitive. You don't want any other host to be updating the LUN at the same time. And this is used for critical metadata operations. For example, if you're doing a timestamp update for a particular file, when you're updating the timestamp, you don't want anybody else to access that particular information. So you put a log, you update the timestamp, and then you release the log. And this is all done in a very granular fashion, like in the order of few hundred microseconds, very, very small logs, micro logs. But when you do VMIO, SCSI reservation is not happening. When you do VMIO, each VM does IO on its own data. So there are no metadata operation when you do VMIO. So you won't see this when you do just do VMIO. But if you're touching files, if you're creating new files, you're allocating new space in your file system, then you can see SCSI reservation being placed by that particular host because it was doing some metadata critical operations. Conflicts per seconds basically tells you if I'm doing SCSI reservation, at the time of SCSI reservation, any other IO which is happening will be denied by the LUN. The LUN would say, I'm busy. I can't take your IO right now. So you have to retry those IOs. So that is called as SCSI reservation conflicts. So in an ideal scenario, the conflicts value should always be 0 because you don't want your IO to be retried because there was some busy factor, right? Later in the presentation, I have a slide which explains how to troubleshoot problems for these kind of scenarios. Okay. The other interesting thing that we added in 4.1, of course, we added a bunch of interesting things in 4.1. I don't know why we called it 4.1. It's vStorage API for array integration. So what this does is, instead of doing certain operations through ESX host, we can actually offload the work to your storage array. When you are cloning a VM, for instance, when you clone a VM, what you do is you read the VMDK file from the LUN to the ESX host, and then you write it back to the LUN, to the same LUN. The data is already there in the LUN. You're reading it and you're writing it back. So you're creating unnecessary traffic between the LUN and the ESX host. Instead, we can tell the array saying, you know what, why don't you copy the data on your own? Duplicate it for me. And then the array will come back and say, yes, I've done it, finished. That saves a lot of traffic between, when you're talking about like 64 gigs files or huge files, right? So this is something that we've been working with the storage vendors, all the storage vendors, and we have an API for it. It's called the vStorage API. In fact, there is a talk on that topic. I don't know if there's a talk today, but the talk was there in the last few days. And it actually goes into the details about how this is implemented. So this is not just for cloning operations. We're using this for a lot of other things too. For example, you want to write zeros into a particular file. Again, you don't have to go and write zeros. You tell the array, you write the zeros. Arrays goes and writes zeros for you. So that's the operation. So we have stats for those. It tells you how many clone write requests the array has sent, how many has failed. So if your array does not support it, it will come back as failure, but we'll retry it again, hoping that you updated the firmware of the array. So for this feature to work, you probably need an updated firmware on the storage array side. Then we also have ATS command. So ATS command is similar to SCSI reservation, but it's much, much more efficient than SCSI reservation because this is handled internally by the array. So that's also supported, and zeroing, all these things are supported. Again, I have an example later in the slide to showcase this. Then we added stats for NFS, which a lot of people have been asking for it. I think this also was backported to ESX 4.0, even though this is new in 4.1, this was backported to 4.0. So where we show all the NFS statistics. But one thing I want to point out is, for NFS, we only show the end-to-end latency. We can't predict the latency from your device to the LUN. End-to-end latency, G average stands for end-to-end latency. That is latency as seen by your guest OS. That's the only latency we actually show. We don't show the other two latencies because it's very difficult to track latencies when you're using TCP/IP for your transport layer. Okay. This is a very subtle point. It's mostly an internal change. You probably don't need to worry about this. So previously in this screen, we used to report I/O statistics of a particular VM by filtering out all other I/Os, which is originating from a different source. We only narrow down to a particular source, but we changed it to something called as vSCSI stats. You don't have to worry about it, but if you have questions about this, you can come and talk to me personally. All right, so that's ends that section. So I'm going to jump into the troubleshooting examples. So the first example I have is 2 Linux guests, and they are exactly identical Linux guests in most ways, but I'll point out one difference. But they have different CPU utilization. One is using 7%, and one is doing 2%, and these are completely idle VMs. So why would 2 idle VMs, exactly identical, consume different CPU cycles? So the clue is this particular counter, timers per second. So timers per second tells you what is the timer interrupt rate this guest OS is demanding from VM kernel. So timer interrupt is the way the operating system programs timer interrupts to measure time. So they'll say, give me 1,000 interrupts per second. And if you deliver 1,000 interrupts per second, then it'll assume that 1 second has elapsed. So that's how it measures time. You can either program saying, give me 1,000 interrupts per second, or you can say, give me 100 interrupts per second. And then you can count only 100 interrupts, and you know 1 second has elapsed. But in a virtualized environment, this is all delivered by the VM kernel. So you have some overhead in delivering these timer interrupts. So if you are asking timer interrupts at a much higher rate, you're going to have higher CPU utilization. So that's what is happening in this case. In this case, one VM is requesting 5,000 timer interrupts per second. The other one is requesting 500 timer interrupts per second. The reason why there is a big discrepancy is that Red Hat, by default, uses 1,000 timer interrupts rate. That is per vCPU. If you have a 4 vCPU VM, it is 4,000. On top of that, you have to add one more 1,000 interrupt rate for local epic. If you're using an SMP kernel, you have to deliver one more extra 1,000 interrupts. So that's why it's 5,000. So it's a 4 vCPU VM, and that's why it's 5,000 timer interrupt rate. But Red Hat also provides an option where you can reduce this timer interrupt rate by passing a kernel boot option, which is called divider equals 10. And that kernel boot option reduces your timer interrupt rate by 10. So that's why it's 500 Hertz instead of 5,000 Hertz. So this is something that we recommend as a best practice. So that was applied on one VM and was not applied in the other VM, and you can spot that out from using ESXTOP. Okay, the number of worlds 7 tells you it's a 4 vCPU VM. The other way to reduce the timer interrupt rate is you reduce the number of vCPU count. You make it as a 1 vCPU VM. And now you see only like 2,000 timer interrupts per second. All right. Then what about Windows guest? The Windows guest can also ask for an increased timer interrupt rate. The default for Windows is 82 Hertz. But in this screenshot, you see 1,000 Hertz has been requested. This is because if you run some multimedia programs inside the guest, the multimedia programs can reprogram the timer interrupt rate to a higher rate so that you have much more granular measurement of time. So that is why it happens. That concept is called multimedia timer. So this was added historically in Windows for MIDI file support and stuff like that. I don't know if any programs are using it in the current generation, but if you're using some Java programs, the Java programs can import certain classes which might use this functionality, and it might increase your timer interrupt rate. So this is very common if you use Tomcat in your environment. Most likely you would see this will be using 1,000 Hertz. So you go and fix the problem. It becomes 82 Hertz, and you also see that the CPU utilization drops because you reduce the timer interrupt rate. So this is useful if you're like really, really conscious about how to reduce your CPU consumption. You want to do more consolidation, put more VMs on the same box, and those kind of exercises. For many people, if you don't care about this idle CPU utilization, it's fine. You don't have to worry about this. Okay, then I want to give you an example for CPU clock frequency scaling. This could be a little confusing, just a warning. Okay, there are 3 different metrics: percentage use, percentage util, and percentage run. Percentage use is the CPU usage with reference to the base clock frequency. So example is, if your capacity of your processor is 3 gigahertz, the base clock frequency is 3 gigahertz, and if you use all your 3 gigahertz, then it's 100%. But if you're using more than 3 gigahertz because of turbo boost, like 3.5 gigahertz, then your use will be greater than 100. If you're using 1.5 gigahertz of 3 gigahertz, it will be 50%. Okay, so that's clear. That's with reference to the base clock frequency. Percentage util, on the other hand, is CPU utilization with reference to your current clock frequency. Your base clock frequency could be 3 gigahertz, but power management can kick in, and the P states can change, and can put your clock frequency at the current rate as 1.5 gigahertz. Let's say your processor is currently at 1.5 gigahertz, and you're using 1.5 gigahertz. Then util will be 100, because you're with reference to the current clock frequency, you're using your max, so that's 100. But used will be 50%. because your maximum capacity is 3, and it's 3 gigahertz, and you're using only 1.5. So you used to think from a capacity point of view, what is my processor capacity, how much of I'm using it right now? Util is how much I can use, now what am I using right now? I can use only 1.5 gigahertz because my current clock frequency is 1.5 gigahertz, and if you're using 1.5, my utilization is 100. You utilize what you can. But use is what is the capacity that you have, what is the headroom you have. So that's the two things. The reason this is important is if you have power management enabled, sometimes your CPU utilization numbers can be a little tricky to understand. I know it's really confusing, but unfortunately, power management messes around with your clock frequency, so you have to recalibrate everything based on the current clock frequency. Percentage run on the other one, it tells you what is the CPU schedule time, how much time this VM was running on a particular CPU. So here, the example here is, here the VM has been running 100% of the time. The percentage run is 100, but the percentage used is 74. Any guesses as to what's happening? Okay, I'll give you the answer. Used is with reference to the base clock frequency, right? You're running all the time, but you're only consuming 74% of your processor capacity, which means your processor clock frequency has been dialed down. So your processor is running at a lower clock frequency than what is capable of. So that's a clue, because the clue here is basically the run time. Run tells you that you're running at 100%, which means ideally you should be 100% used, but you're only using 74%. All right, to make things even more confusing, we have hyperthreading. And in this case, I have 2 VMs, both running at 100%, right? Looks perfectly okay. And you look at a line called core utilization. The core utilization is the utilization of your CPU cores, excluding your logical CPUs. So if you have hyperthreading enabled, you have 2 logical CPUs per core, right? So in this screen, you have 8 CPUs, which includes the logical CPUs. But you have only 4 cores, which means you have hyperthreading enabled. So it tells you here that both the cores are being busy, is being actively being used. So it's fine. 2 VMs are running on separate cores. Everything is perfectly fine. This is the default behavior. VMware scheduler always tries to put your VMs on different cores as much as possible, so that it doesn't try to put them on the same logical CPUs if you have free physical CPUs on the other side. But this is a crafted example. So I set CPU affinity, and I made both the VMs to run on this logical CPUs of the same core. So here, both the VMs are running 100% of the time, but percentage use is less. Now, in the previous slide, I said if percentage run and percentage use doesn't match, it means your clock frequency could be scaled down, right? But in this case, clock frequency is not scaled down, but you still see the percentage used to drop. That's because you're doing core sharing. You look at the logical CPU utilization, both the logical CPUs are constantly being used, but they're sharing the same core, underlying core, and the core utilization is only 100. So this is the reason you see the use count is reduced. So 2 VMs are sharing the same core, and they're running on the logical CPUs. This also translates into the latency value that here it shows. It says 31%. Basically, it shows that the VM was not scheduled for 31% of the time because you were doing core sharing. Okay, I know this could be a little confusing. Go back and revisit the slides. I think it might make sense. I'm trying to pack as much as information into this talk, so I know it might go a little over your head. So let me pick up a little bit of space. I'm running out of time, I guess. So this is about memory reservation. So this VM has got 4 gigs of memory reservation, as shown by AMIN. AMIN stands for assigned minimum memory for this VM. So it has 4 gig memory reservation. The total memory reservation on the host is 7 gigs. The free memory reservation is 630 gigs. Okay? Everything looks cool, right? Now, ideally, under this scenario, I should be able to power on a new VM, let's say a 512 meg VM, And I can set full reservation to the VM, and the VM should be able to power on because I should have 633 megabytes of unreserved memory, right? But the VM power on fails. It fails with the error message saying the requested reservation is some number of pages. Now, if you do the math, you basically multiply the pages by 4 KB size. That amounts to 820 megs. So why would a 512 meg VM and with full reservation would need 820 megs of reservation? Any guesses? There you go. That was correct. So every VM which gets powered on has an overhead memory associated with it. The overhead memory depends on whether it's a 2 VCP VM or a 4 VCP VM, whether how much memory size you're given to the VM, and whether it's 32-bit, 64-bit. There's a whole sort of combination which decides the overhead memory. And the overhead memory has to be reserved always, in addition to the guest memory reservation that you're setting. So in this case, the overhead memory is like around 348 megs for this 512 meg, and that's why it was not powering on. Now, if you set the guest memory reservation to 0, then the VM would power on. That's how I powered on the VM in this case. All right. SCSI reservation conflicts. I mentioned that, I'll mention this. So this is a Red Hat 5 VM. It's doing a lot of IOs, around 1,000 IOPS. And it's getting very good throughput, 110 megabytes per second. Really, really good throughput. Look at the latency for this throughput, just 1.38 millisecond, extremely good. This is like a beefy storage and everything is good. Now, suddenly the throughput drops, the IOPS drops, the throughput drops. How do you know this throughput drop is because of a storage array problem and not because of the VM itself is not issuing the IO? How do you differentiate it? The way you differentiate is by looking at the latency numbers. You know previously it was doing a lot of IOs with very less latency. Now suddenly the latency has jumped. So now the latency shows 10.55 milliseconds. So the reason for that is SCSI reservation conflicts. Again, this is a crafted example. In your scenario, you're probably not going to see this unless you're doing some crazy stuff of like touching every file on your VMFS volume on a different host and doing some IO on the other host. So it shows reservation conflicts. And you look at the commands reads per second, then you see it also has increased now because you're doing retries. Here I'm doing only 149, it's 241 here because you're doing retries. Because when there's a conflict, we retry it. Okay, so that's considered conflict. An example for vStorage API. So here I'm creating a new VM. Whenever we create a new VM, we write zeros for the blocks that we allocate. And those zeros can be written by ESX host, or it could be written by the storage array if you offload the work to the storage array. In this case, it's getting offloaded. That's why these counters are getting incremented. And you can also confirm this by looking at the adapter statistics. And you look at the adapter statistics, the adapter is not writing any IOs at all. Look at the megabytes written by the adapter. Because it's all done in the background by the LUN. You don't have to write zeros from your adapter. So you're basically saving traffic on your HPA. That's the whole advantage of doing this operations using this API. All right. So I just want to quickly run through the other diagnostic tools. We have a bunch of tools for getting scheduler stats. I'm not going to go into this depth. We have tools for memory-related stats. We have tools for getting stats for the FT virtual machine. I'm going to get kicked out. We have tools for collecting SWAT stats. We have tools for vSCSI stats. This is something very interesting. I'll give you a brief overview. So vSCSI stats is a tool. It's collected from your virtual SCSI layer in the VM, where we can collect histogram details as to what is the IO size on average I'm seeing? What are the different IO sizes that I'm seeing? What is the latency distribution that I'm seeing? Out of the 100 IOs that I issued, how many IOs fall into less than 5 milliseconds? How many IO falls into greater than 10 milliseconds? You can get advanced diagnostic information using this tool. Quick screenshots, vSCSI stats -L gives you all the virtual machines on your box and the virtual disk it has. And then you can ask for latency information, and then it'll tell you the latency information in this histogram fashion, which tells you, you know what, out of these, all the IOs, 5 IO is greater than 10 milliseconds. This is in microseconds. It tells 5 IO is greater than 10 milliseconds. And similarly, you can get IO size stats. It here says all your IOs are 2K blocks. Yes? Yes, for 4.0, we didn't ship the viscosity stats, but we updated a blog article with a link to the download. For 4.1, it is ships with viscosity stats. So that's all I have, and you can come and talk to me if you have additional questions. And thanks very much for coming to the talk.